All right, next up in our short chapter series is chapter 2. This is just about different ways to organize data. And so what I want to do is let's talk about variables and data. So a variable is just some sort of trait that varies from one person or one item to another. Qualitative variables are things where there's not numbers attached to them. So things like hair color, eye color, and so on. Quantitative variables are variables that do have numbers attached to them. So that's things like height or weight or age or whatever, something where there's a name attached to it. A discrete variable is one where, so discrete basically means that you can write down all the characteristics in a list. It's kind of like a listable variable. A continuous variable is one where you cannot write down all the values in the list. You just have kind of a continuum of values that you can take. So you know that your value is going to be somewhere between, say, 5 and 10, right? And then any number in between 5 and 10, maybe 6.7943, whatever. Um, that's going to be a continuous variable. So continuous variable means that you can take a value in this interval, in anywhere in the interval. A discrete value means that you're either here or here or here or here, and you can kind of write down and list all the different values. So it's that's the distinction that's made there. So discrete versus continuous. All right. Um, so variables are traits that vary from one person to another. Data are values of the variables. So again, you can have qualitative and quantitative data. Again, qualitative data are values of variables that do not have numeric values. So again, eye color, hair color of a person. Qualitative data could include something like what's the capital of each state, right? There's some sort of information there, but it's just not numeric. That's all. And then quantitative data is, again, data where there are numbers attached to it. So it could say the population size of each state, whatever. Okay. And again, same discrete continuous distinction that we made before. Discrete means that you have some sort of list of values that you can take. Maybe you have 5 or 10 or a million different values that your variables can take. Continuous means that you have infinitely many values in some range, right? So you have some sort of continuum of data there. So those are going to be big definitions for us as we go along. We're going to concentrate mostly on quantitative data. Quantitative data is going to be, so again, the values, the data where you can have a numerical value attached to it are going to be the data that we care about the most, or the data that we work with the most. Qualitative data is still useful. We just don't have as much tools to deal with it. Okay, so so again, we will focus more on quantitative data throughout the semester. With that being said, there's a little bit that we can say about qualitative data. So one thing that you can do is record what's called a frequency distribution. So if I wanted to talk about hair color or eye color or some other non-numeric value associated with each student in the class, I could write that down and we could say there's whatever, 10 people that have brown hair, 15 people that have blonde hair, 10 people that have black hair, and so on, right? So you could have a frequency distribution, and that's one way to organize qualitative data. The example that this book goes through is party affiliation. So again, that's a non-numeric variable. So Democrat, Republican, or other, okay? And it's discrete. You could have a relative frequency distribution. So that's going to be basically the same as the frequency table, except you divide each number by the total size of the group that you're working with. Okay, so that's the relative data. So for example, for the party affiliation example that they had 13 Democrats, 18 Republicans, and 9 others for a total of 40 people. So that gives these different relative frequencies, 0.325, 0.450, and so on. You could have a pie chart. Again, this is a way that you can organize qualitative data. You could have a bar chart with the relative frequency or even the frequency on there. Okay, but again, we're going to focus mostly on organizing quantitative data. So this example is the number of TV sets in 50 randomly selected houses, right? So that's going to be some sort of discrete numeric value. And what you can do is you can write down the different values that we get from our sample. So this is, again, kind of thinking about inferential statistics. We're not looking at all the houses in the US or all the houses in the world that have a TV. We just took a sample of 50, wrote down how many TVs they have, and then that's the list that we have. So the frequency and relative frequency distributions, we can do the same there. So you can think about how many households had 0 TVs, 1 TV, 2 TVs, and so on. And that leads to the following frequency and relative frequency tables that we see here. And you can also do a tally if that helps. And one of the things that's going on here that I think is worthwhile is this is what's called binning or limit grouping. So binning, or putting in different bins, means that you are still talking about quantitative data, but it's kind of a clustering of the quantitative data. So you're taking the different data and you're putting it into different groups, and then you're saying how many times does each group appear in the data. So for example, if we go back to the TV example, what we could do is we could have, say, different clusters where you have 0 through 2 TVs. That would give us a frequency of 1 plus 16 plus 14 is 31. And then 3 or 4 TVs would give us a frequency of 15, and so on. So you could have different clusters within this. So there's, again, different ways to organize all this data. And that kind of leaves a lot of choices up to us as to how we want to organize our data, how we want to present it. Okay, but that also leaves a lot of opportunities for us to inadvertently skew the data. So again, we need to be very careful not to introduce bias. How do we decide what clusters there are, right? We should probably decide what the clusters are going to be before we get any values in our survey. That way, the values that we actually get in our survey aren't biasing how we're choosing our clusters, right? So these are the kind of choices that we're going to have to make as we go along. Okay, so anyways, that's called the limit grouping or binning. And there's the lower class limit, which is the smallest value that can go in a class, the upper class limit, which is the largest value that could go in a class, the class width, which is the difference between the lower class limit and the upper class limit, and then the class mark, which is the average of the two class limits of a class. So let's go back. And if I think about the days to maturity here, this is an example that was taken from our book. It's about 40 investments that we have in the days for the investment to mature. The different bits of terminology that we had, the lower class limit and the upper class limit, that's going to be in this column here on the left, the days to maturity. So the lower class limit would be 30, and the upper class limit would be 39. The class width would be the difference between the two, so 39 minus 30. And then the class mark is the average of the two. Okay, so that's what they're talking about there. That's for the different classes. All right. Again, when we're talking about grouping, there's different ways to do that. So there's single value grouping, which is very frequent. The only thing about single value grouping is that if you have a very large data set, sometimes it's hard to, if you have 10,000 data points and you want to know how many different TVs there are in each house, that's probably fine. But if you have something where there's a lot more variability and you want to look at, say, what's each person's weight down to 1/10 of a pound, you're going to have a lot of values that are just achieved by themselves, right? So you're going to have a lot of values. Maybe there's only one person that's 180.3 pounds, but there's a lot that are in the 180 group. So sometimes it's better to group data. And so single value grouping is where you just have it's where you have a discrete variable, and each possibility of the discrete variable goes in its own category. Limit grouping is where you have, so it's a type of cluster grouping where you have, so limit grouping is where you have, say, your weight's going to be whatever, 120 to 130, and then 130 to 140, and so on. Okay. And then cut point grouping is actually, it's basically the same as limit grouping, but it's going to be used for continuous data. So cut point grouping is saying, all right, you have a continuum of values. We're going to say from here to here is one group, and from here to here is another group, and so on. From here to here is a third group. So you have these places where you have to decide where to cut the data because it's continuous. But it's basically just clustering like we talked about in the other examples. All right, a few other ways just to represent the data are with histograms. Histograms, again, are a pretty familiar thing, so I don't feel the need to say too much there. You can have a frequency histogram or a relative frequency histogram, depending on whether you're talking about the actual number or the relative frequency of whatever item or whatever variable you're discussing. Okay. You could have, again, here's our limit grouping example where you have the 30 to 39, 40 to 49, and so on. And again, you can have a frequency and relative frequency histogram there. And then cut point grouping. So this is the weight example where here they're thinking of the weight as being a continuous, you have kind of a continuum of values that you can have for your weight. Really, there's no reason to round to the nearest tenth of a pound, like I said before. So you can really have any value that you want. So you can think of that data as being continuous. And then you need to decide what are the cutoff points for where you're going to have your different groups. All right. A dot plot is going to be a graph where each observation is plotted as a dot. And so the way that this looks, I think it's just better to just do an example. Here's 16 data points. And a dot plot here is you're just going to put each data point and represent it with a dot. And if that data point gets realized more than once, so if you look at this table, 199 is on that table 3 times. So if you look at that table, 199 is there 3 times. So that means that 199 is going to have 3 dots on it. Okay, so if you look at on the ticks at the bottom where 199 is, you're going to have 3 dots on there. Okay, so that's called a dot plot. It's really not much more to say there. There's what's called stem and leaf diagrams or stem plots. And again, I think this is best just represented with an example. So here we had the same 40 short-term investments and whatever the number of days to maturity was. And so rather than writing out each number, 70, 64, 99, 55, and so on, what you can do is you can put down what are called stems and leaves. So the stem is going to be everything but the last digit. So in this case, it's going to be the tens digit. And so that can be a, let's see, the values go from 30 something to 99, it looks like is the largest. So that means that your stems can go from 3 to 9. So your tens digit can be a 3, 4, 5, 6, 7, 8, or 9. And then, let me see if I can draw here. I want to be able to draw here. So if we look at the 87, what we're going to do is we're going to put down an 8 in the stem and then a 7 in the leaf. Okay, so that's how that's going to work. Okay, so that's how this stem and leaf plot is going to go. And then if we have, let's see, a number that appears more than once. So if we look at 99, the way that we're going to represent that that number appears more than once is we're going to put 9 down as our stem, but then we put 9 down as a leaf twice. So that represents that 99 is there in the list twice. Okay, so that's how that's going to work. And again, if we have, that was for 2-digit numbers. If you have 3 or even 4-digit numbers, the story's the same. Generally, the leaf is just going to be your units digit for whatever variable you're considering. So here, if we have a 3-digit number, we're going to have the first 2 digits will be the stem, and then the last digit, the units digit, will be the leaf. Okay, so that's how that's going to work. Finally, we'll talk a little bit about distributions. So distribution is going to be, if we think back to the histogram and kind of the shape of our data, whatever that shape is, that's what a distribution is. Okay, so it's going to be a table, graph, or a formula that gives us the values of our observations and how frequently or how often they occur. So you can have bell-shaped distributions or normal distributions, and we're going to talk a lot about these bell-shaped distributions. There's a few other shapes that come up a lot, but just a few others. There's actually, before I get to the shapes, I'm sorry, there's what are called unimodal, bimodal, and multimodal distributions. That just tells you the mode, which is something that we'll talk about in chapter 3. The mode is going to be the most frequent value. So in our case, we have the most frequent value appearing once. Here, the same value appears twice. And then here, our most frequent value appears 3 times. So that's called multimodal. And then these are the shapes that I was thinking of. There's the bell-shaped, which is kind of the classic normal distribution shape. There's the triangular distribution, which just makes that triangle, or the uniform or rectangular distribution. Okay. There's also what's called skewness of distributions. And the right skewed or left skewed, the skewness tells you which side of the distribution has a longer tail. So if it's right skewed, that means that the right side has a longer tail. Okay, so there's a long right tail. And for left skewed, that means that the data has a long left tail. Okay, and so there's systematic ways to talk about these. We're not quite ready for that yet, but here we are. So again, a few more examples. There we are. So a few more examples. And that's really all I wanted to say about population distributions and shapes. I guess there's one other nuance here, and that's talking about samples and populations. So with a population, remember the population is all the data points under consideration. The sample is just some small subset of that. And so if you have a population, and then you take different samples, your samples themselves might have a different distribution than the underlying population, and that's totally okay. So if you ask 100 people who you're voting for in an election, you might get a slightly different response than if you take all, whatever it is, 100 million eligible voters in the US and ask them, right? So you might get a different response from a sample. But the larger the sample, the closer you're going to get to the original distribution. And there's a way that we can make that precise, and we will. Okay, so that's all I wanted to say about population and sample distributions. All right, this final section is just about misleading graphs and how we have to be very careful the way that we organize our data. And this again just goes into the idea of trying to ignore bias, trying to get rid of all the bias that we have possibly in our statistics. So this again just goes to and speaks to that idea. I'm sorry, I'm slightly distracted. I don't know why my presentation says Tuesday, January 9th. It's August. But anyways, we'll leave that alone as it is. So misleading graphs. So we want to just be sure that we're representing our data in an unbiased as possible way. And so you can think about, we have 2 kind of good examples here. One is both of these are perfectly true graphs, and they kind of give you an idea of what the unemployment is doing at any given time and whether it's increasing or decreasing and roughly what it is. This graph on the left, okay, so this graph over here really highlights whether or not the unemployment rate is increasing or decreasing from the month before, okay? That's really what it's doing best. And that's why we would want to use that graph versus the other. The other graph isn't telling you much about the change. It's telling you roughly what is the unemployment overall. So here on the left graph, it looks like the unemployment in March is drastically less than the unemployment in January. And that drasticness really doesn't look that drastic when you look at the entire untruncated or non-truncated graph. Okay, so we just have to be careful about which is going to be the appropriate graph for the occasion. Do we want to talk about the overall value, or do we want to talk about whether the unemployment has gone up or gone down? Okay, that's really the discussion there. And then the last thing is just about improper scaling. You have to make sure that uh, you're not kind of misleading with any kind of graphical example. So I'll just leave this to you. I'm not going to say too much more about it. Okay, but again, we need to be very careful not to introduce bias in our data, either when we study and when we kind of group all these variables together and run statistics on different sets and different studies, or when we present those statistics. So even after we run all the studies that we want, we have to be very careful about how we portray all those studies. Okay.